I am really looking forward to today's seminar. Our first speaker is going to be Professor David Elliott. Now, he is Professor of Technology Policy at the Open University and co-director of the OU Energy and Environment Research Unit. Now, he has developed courses on technology innovation, focusing in particular on renewable energy technologies. So he really is absolutely the right person to start the day. And he has written extensively on UK sustainable energy policy. So, Professor David Elliott, thank you.
One of the issues I'm going to pick up is scale. I'm going to move from small to global, which is why the title there. It's the rough agenda. None of you, of course, know anything about energy and climate change, so I'm going to have to give you an introduction to that. Perhaps you know a little bit less about the actual decarbonisation options, and I'm going to look at those and then look at these issues, leading from the small to the large scale. Quick run through. We all know the story. We've been using lots of fossil fuels. Rate of fossil fuel use has gone up with the industrialisation process. One of the possible issues that's been worrying people for the last few decades is the imminent shortage of, or scarcity or increased price of various fossil fuels. That's at traditional oil and gas peaks, but people have been also talking about coal peaks and maybe even uranium peaks, solid material peaks of resources. But long before we reach that, it's argued, well, maybe before we even try to reach that, we should stop using these scarce resources because of the other big issue, which is the climate change one. The debate is out whether climate change comes first or peak oil comes first. You know the climate change story. The level of emissions has shot off the chart, and it looks like the temperatures are following, although we can't be certain quite how tightly they're following. Predictions, though, show us going up into the 4s and 5 degrees unless action is taken. So that's our starting point. Does it matter? I mean, if it didn't matter, we could just enjoy the ride. This is on the left here is what happens if all the seas expand at 6 degrees and all the ice caps melt. Which means Birmingham becomes the capital of the UK, which is enough motivation, I think, to make anybody act quickly. On the right is the sub-story for the Guardian front page as to another reason why you might want to respond, but carries less immediate impact as far as I'm concerned. But the financial argument, this economic argument, is also strong. The control cost, the cost of doing something, is less significantly than the cost of not doing something, by something like a factor of 10 or 5, depending how you want to do the sums, according to Stern. In which case, action taken now makes sense. There's a reason for moving quickly, because carbon dioxide has a long residence time in the upper atmosphere, despite the interchange between sea and sky, much longer than methane. Effectively, once you put it up there, it's there for a long time. If we stopped at year 0 or 1900 there, we'd still be at more than half levels many hundreds of years later. So the earlier you start making reparations, the better. And the longer you leave it, the more it's going to cost you. So urgency is the issue. Engineers look at pictures like this on television, and the voiceover says, climate change. And they say, well, there's an awful lot of steam going up there, yes. That's not much of a problem. Well, it's a little bit of a problem. But actually, the real problem, as you know, is coming out the chimney in the middle. But also, we've come back to the issue, this steam is also another giveaway. If you're an engineer, you say, oh yes, why have we got this vast amount of steam coming up? We'll have a look at that in a minute. The elephant in the room that I keep trying to bang on about is that we keep talking about aircraft and power stations and cars. We forget that every single house has got a down-grade gas boiler sitting in there, churning out carbon dioxide in your own home. Probably about, 40% of total carbon dioxide is coming from this machine in the corner of your basement or wherever it is. And yet we don't mention that much. Gas boilers, even combi boilers or condensing boilers or whatever, are a major source. But of course, we're all familiar with the guilt-tripping aircraft and car use arguments for climate change. Those are the three big areas anyway: power stations, gas, and transport. What can you do about it? Here's a list of actions. Sequestration, somehow or other capturing and storing the carbon dioxide, using lower carbon fuels, switching to gas from coal, which is 40% change if you're doing it in an advanced combined cycle plant. Generate the energy more efficiently, stop avoiding so much steam, combined heat and power. Use fuel more efficiently when you actually produce them, get more use for less energy. Use non-fossil fuels. The two obvious and only at the moment options are nuclear and the various renewables. Then there's a whole series of social solutions, which I'm not going to look at. Steve Peake later may talk about some, which is we use less or change our lifestyles to use energy in different ways. And then finally, there's another area of adaptation. If all the above fail, we just take it on the chin and see how to adapt our way of life and our planet and our living style in response to climate change. Now, the more you look at this, the less chance there is of being able to adapt to the scale of change. If we're up to 6 degrees, then the scale of adaptation becomes probably beyond what most countries could afford and what most people can accept. So I tend to want to treat these as not just first tries. These are desperately important, all these earlier stages. We can't just sit back and wait to adapt. Obvious thing, sequestration by trees. We've been doing that for centuries. The planet's been doing that. We've, of course, cut down a large proportion of the trees, which doesn't help. Even if we replaced all the trees we've cut down and then again replaced them again and again, we'd still only be adding up to 15%, something like that, of the climate change issue. It's a part solution and it's fairly cheap. Growing trees is not expensive. You need the land, but it's not to be forgotten, but it's not the magic bullet. Magic bullets do appear. Stephen Salter and other people have come up with the last-ditch stands. If all else fails, let's change the geotechnical quality, geoengineering of the planet to bounce off sunlight from the upper atmosphere by shooting up water vapour so you get increased blackening, whitening of the clouds, that the clouds have bounce off sunlight, change the albedo of the atmosphere, or put microparticles in the upper atmosphere through satellites, all sorts of fairly exotic schemes, all of which are extremely expensive, some of which might actually technically work, but nearly all of them have gigantic and unknown environmental impacts. You're talking about changing planetary systems with impossible to model the long-term implications. You'd have to be really desperate to press the button on any of these. Similarly, slightly panicky, let's grab the carbon dioxide at the back end of power stations and stuff it underground.
I think there was just a question in terms of the size of the towers.
Yes, the previous slide.
The scale of the towers that you showed us on the previous slide.
I think that this is a sort of size of a major cruiser, not a sort of full battleship, but something like that, big. No people. Remotely operated. They cruise around the sea, the fleets of them, hundreds of them, cruise around looking for crucial places to... I'm trying to be straight-faced here, but I do find it a little bit wacky. These rotating towers generate the energy to squirt the water vapour up into the sky. There's tidal energy connected to drive it around. It actually steers itself around. The idea is to find places where you can have maximum impact, because you want to avoid precipitating rain in some areas. Other areas you do want to. You're doing climate modification on an international scale. So the sums look. In energy terms, it actually does work. You could do it. Sorry. Carbon capture and storage. I mean, there's a symmetry about that. So we let these people in. They're sort of waffling around here. Seems sort of symmetrical to take some oil or methane out and then burn it and grab the carbon dioxide and stuff it back down again. There's a sort of symmetry, but otherwise, in engineering terms, it seems pretty inelegant to try and drag stuff out of the exhaust of power stations and stuff it underground under pressure and hope it stays there. The attraction that it allows the oil companies to carry on much as before, except it now costs them twice as much. So there's the attraction of carbon capture and storage allows the show to continue for a period. I find that a little bit evasive. This is really bad engineering, sticking something on the end of the pipe and squirting it into the ground. But it can be done, and I'm sure it will be done, because it allows you to carry on burning coal, oil and gas for some period. Much more technologically sweet, if you like, is dealing with the problem that's nearer to the source and avoiding energy waste in-house and other buildings by all the obvious energy-saving building envelope design and add-ons to improve the energy efficiency. I mean, Finnish Minister of Energy came over a few years back to talk to us and said he couldn't believe that 6,000 old-age pensioners die in Britain every year of the cold. He said in Finland it gets cold and people die, yes, but never indoors. He couldn't imagine how we could have buildings that would kill people. So there are things you could do to improve buildings. And this country, having just a low starting level, there's a lot of room of gain there. But however much you save, you're still going to need new carbon-free or low-carbon energy sources. And the obvious options are the renewables. Here's some eco-porn pictures of wind turbines you'd luxuriate on. Increasingly going offshore. With the obvious thing, get rid of sticking wind turbines up in the air, stick them underwater, get much more energy out of an underwater wind turbine. Water's 800 times the density of air, so you get a lot more bangs per buck. Tidal energy is harder. You're dealing with an interface between air and water, which is chaotic at the best, whereas underwater water turbines, you've just got 4 movements of the water every day in a nice laminar flow 20 feet under the surface. Submarines are much easier to build than ships. They don't have to take so many stresses. Some examples of underwater wind turbines or tidal current turbines. The big area, I think, of development is Britain's strong card. We have a very big resource of horizontal tidal flow, and we fortunately seem to be at the front of the technology of that at the moment. There are all the other obvious renewables too, solar heat and solar electricity and indirect solar in the form of biomass energy crops. Stick all those together, what does it look like? Here's a fairly conservative view from the government's Carbon Trust ETI, as it was. Very roughly, add them together, somewhere around 50% of UK electricity by 2050. Now those sort of numbers kick around for most countries, and this is now looking fairly conservative. You could pretty much 50% by 2050 seems to be the going rate for most industrial countries can achieve that if they want to. And of course a lot more. This is just the relatively straightforward approach. So that's your ballpark, half electricity by 2050. Now, we may need to do a lot better than that. The price is the other thing that is interesting. That's dropping as you would expect as the technologies physically develop and the markets for them expand, the unit cost goes down. Here's an American NREL study showing the percentage drop since 1980, with wind dropping very fast, biomass not so fast, PV very fast. The UK Cabinet Office did a study. Some people here, I think, were involved with it. I was as well, briefly. For 2020, electricity prices for the various options. So you can see the renewables all looking very competitive. The more traditional coal, gas and nuclear looking not so competitive. That was a few years ago. Here's the most recent study I've come up with showing long-term costs, sort of learning curves basically, by 2050, with PV the most dramatic reduction in price, photovoltaic solar dropping very rapidly. This, interestingly, is from Iran, should you be interested in taking an interest in renewables. Most of the fossil fuels are seen as just sort of chunking up in 2% a year price increases. Okay, here's where I'm going to try and move a quick look at the renewables by scale. The full shopping list looks like big stuff, but in fact, small stuff equally important, or can be equally important. So the scale is house level, the city level, the country level. So at the house level, people often argue small is beautiful. Small generators can be nearer to the load, therefore there's less losses in the transmission. You can overstate the losses in transmission, long-distance transmission, maybe 10% over thousand miles. So building a technology into a house has some attraction. And as you'll be aware, the last few years we've seen a whole range of so-called micro-generation technologies, micro-wind, PV, solar itself, solar heating, small-scale combined heat and power, and heat pumps and fuel cells and all other mixtures of not totally renewable, partly fossil fuel-fed options, but all small, kilowatt-sized machines to be built into houses. And there's a lot of talk about this. Now, the problem is, back to the engineering again, simple physics of wind generation, it's square of the wind speed, square of the diameter of the blade, cube of the wind speed. That means if you go up, you get a vastly more increase in power. If you go down, your power drops off very rapidly. So a tiny wind turbine, the 1 to 2 kilowatt, the iPod of the micro wind world is the machine up there. You're going to get very little energy out of it, particularly in urban environments. The Building Research Establishment study suggested that the small turbine on top of a building like that, and that's a particularly good site, that's a tall building. In many urban environments, you're not going to get enough power to pay back the original energy debt, the materials and carbon invested in the construction, much less the actual cost debt. So the initial enthusiasm for micro-wind is somewhat reduced, but there are locations where small-scale wind will work. PV, a bit different. There's no scaled issues on that. You can have it any size you like. Volume efficiencies. Solar heating, again, there are some scale attractions. Very large solar arrays across a whole row of buildings where you share a heat store, because this is a Danish, heat store, gives you some advantages. If you have a heat store scaled to 20 houses, you get much better storage capacity than if you have 20 individual heating units, because the volume and area effect are different. But small is clearly not always beautiful. Interesting report from the Energy Saving Trust last year saying basically until you get up to about 500 houses, the costs are not prohibitive, but around about 500 you start getting advantages. What they're basically saying is that the community scale is the best scale to operate on if you're talking about localization of technology. Community scale, depending on how you define community, small enough to be technically located locally, but also big enough to be reasonably economically efficient, small enough to be locally controlled or possibly even owned, possibly even managed, but big enough to be not a waste of time in engineering terms. Here's the Energy Saving Trust data. You can see the purple is for a large community of 100 or more people. Prices for all the technologies significantly lower, particularly in the case of wind, than when you try for individual private homes. So the individual private home, the bourgeois individualism is jumped on from a great height. Community scale technology, this satisfies all community-orientated, decentralist sort of wish fulfillments. CHP, well, micro-CHP also got a fairly big push behind it. The trouble is, the way they've been set up at the moment, they're following the heat load. You run it for heating. Electricity it produces is additional, which means in the summer you're not likely to be running it much at all, which means your overall annual efficiency on the electrical side is very low. So I have a bit of a rethink of the viability of micro-CHP as a total energy system. So we begin to see some of the disadvantages of small scale. If you move up to bigger CHP, it's digging streets up, connecting up big heat loads, which of course has happened widely on the rest of Europe, but hardly at all in this country. Your efficiencies start jumping up dramatically to sort of 70s and 80% total energy efficiency. One area that's done this is Woking in Borough Council, who've CHP'd a lot of their area with a local heat grid and also a local electricity grid. They've decoupled themselves to some extent from the national grid system, providing electricity power on a private wire network around municipal offices and a few schools, hospitals and hotels and things. About 70-odd% of Woking's large buildings now are on the local borough council's energy system, heat and electricity. The result is since they're mostly generating off gas now rather than electricity, they're still importing stuff, it's gas they're using, but they've switched over to using gas for electricity, and that's reduced their carbon impact by a significant amount. But of course they're still importing gas, so it's not an autonomous system. The same for some of the London proposals. The late lamented Ken Livingstone's plan for London was, well, here's the full width of it, but the upshot of it was, at one stage anyway, to get 14% of London's electricity from renewable sources. Not a lot, 14%. When you actually look at the small print, only 4% actually would be coming from internal in London generation. So all the rest would be imported. So what I'm trying to argue is that the small-scale dream that we can do it all locally is very attractive, and we should do as much as we can. But it looks like, in reality, for the moment at least, it's always going to be a small player. There's always going to have to be a lot more imports from somewhere else, the rest of the country to start with, or perhaps further afield. PV solar is the big hope for the future. I'm going for big here. I've mentioned before tidal stream. There's some big tidal stream ideas. Big wind. At the moment we're at, well, there's a 5 megawatt wind turbine being built at the moment. But this is a 10 megawatt design concept. When I let the engineers loose on the drawing board, they come up with, I mean, you asked earlier how big. Here's the cruiser ship now to give you a scale there, right. Big machines. This is a horizontal axis machine, right. You can see the engineering moving on and delivering increasing amounts of power. Big marine technologies like the Severn Barrage, 8.5 gigawatts, or possibly better, a tidal flow system that doesn't block off the whole estuary, where you have turbines that allow just the water to pass through. Costs. Just out of interest, the Severn Barrage up there at £30 billion, the largest civil engineering project a country ever thought of. Very expensive in pounds per megawatt hour. Why you do it, I've no idea. I'm very uncertain about that. Wind around here, nuclear not doing, is sort of in the middle. This is one particular. When you challenge economists, you'll get charts with figures that differ. These at least have got some ranges on. Since I mentioned nuclear, let's just dispatch that to the oblivion it should belong to quickly. Can't help much in the short term, 10 years to plan and build the things. Can't help much in the very long term. There's not enough high-grade uranium to go beyond, well, being optimistic 100 years. If you're talking about dealing with climate change on a significant scale, then you run out of uranium. Not you run out, the prices get very high. In the meantime, between the long and the short time, you're facing all the obvious problems of accidental leaks and emissions, long-term disposal of active waste. I notice Obama has just abandoned the Yucca Mountain project in America, so America still has nowhere to put its waste. Your local friendly Iranians will no doubt be interested in not making bombs from their nuclear power plants, and people have called nuclear power plants pre-deployed nuclear weapons that we've equipped our countries with for terrorists to use. I think that's rather overstating the case, but it is not wise, I think, to have some more plutonium as the basis of your future energy system. I would prefer not to do that if there are other options, and it does seem plainly there are. Most of the renewables are much faster to install. You can put a wind farm up in months. They're cleaner, there are no emissions from wind or solar or whatever. They're safer, not too many people fall off roofs when installing solar collectors, although they do. no emissions, no waste, no proliferation, no terrorist threats, no fuel resource depletion. It seems like an obvious option. People, though, do say, well, yes, renewables is very nice while we sort out fusion. I used to work in fusion for a bit. I always get a bit annoyed when people say this solves the energy problem, A, because there's no waste. Well, no, and everything inside this thing gets fiercely irradiated by inductions. You have to strip out all the materials and store it somewhere. Maybe not as long as, maybe a couple of 100 years worth of radioactivity by induced radiation, but still not a non-issue. Fuel limitations, well, lithium is where you get the tritium from, and we're busily using lithium up in our, well, not just PCs, but cars. And increasingly, there's going to be a battle for lithium in the future. Fortunately, there's lots on the asteroid belt. So if we do crack fusion, we can build spacecraft to go to the asteroid belt to get the lithium to run the fusion reactors. I asked Atomic Energy Authority last couple of weeks back, in fact, a big report they sent me, really surprised me. He said, if we can crack fusion, and they're trying to spend another £20 billion, half the UK's R&D budget and energy goes on fusion, half our R&D budget for all energy goes on fusion. It might, by year 2100, generate globally about 20% of energy. And I don't know about you, I always assumed that, if they crack fusion, this would sort out the energy problem and we could all go home, Then this is the Atomic Energy Authority saying, we're going to have a huge amount of effort. In 90 years' time, we might be able to produce as much energy as we get from renewables now, today. So I thought, this is much worse than I thought. A, it's not guaranteed to work. B, who knows what it's going to cost. C, anyway, I leave fusion, I think, aside as a very uncertain long-term option. Renewables, by comparison, the sunny uplands of renewable futures seem to be being offered to us. This is a recent scenario by Energy Watch in Germany, who are saying 62% of global electricity by 2030. Now, 10 years ago, when we said things like this, people used to fall about laughing, and now we're not laughing so much. I think when you come back in 10 years' time, these sort of figures will start looking standards, but at the moment it's still treated as, well, that's pushing it a bit. But when people say 100% by 2050 of total world energy, people are now still falling over laughing, so that's good. We've got the measure of it. But the falling over and laughing point is around about here. But I think 10 years' time, 100% by 2050 would perhaps be government targets. Who knows? But this is the Infos view from Denmark, with renewables ramping up and energy conservation, of course, taking a big chunk into... there are people here who do scenarios for a living, so I'm aware I'm treading on thin ice here. But here's the actual state of play at the moment. Germany still just in the lead, or it depends how you do the sums. 23 gigawatts of wind, probably more PV than that now. US coming up behind fast, in fact, has overtaken Germany on wind in terms of actual amount of electricity delivered, because Germany's a relatively poor wind regime, America's very good. With Obama in control now, the American targets creeping up, 10% by 2010 and 25% by 2025, still not equal to Germany's target. China, who's much attacked usually for being the problem country, has actually got some quite ambitious targets and huge potentials. I mean, the uplands of central China, 100 gigawatts of wind, easy. You're talking about maybe 10 times that is conceivable. So the sleeping giant could actually be changing a lot. And people attack China for being problematic. In fact, the carbon intensity of Chinese broke through the gap with America about 1998. What this means is you've got a rapidly expanding 8% growth country, in many cases with greenfield site, new technology, being able to outpace a country with pretty old clapped-out capital. So whether they can continue to keep ahead in carbon intensity is another issue. South Korea is joining the game. Huge wind, wind, wave, solar, but tidal stream in particular, and tidal barrage. So altogether there's about 2.6 gigawatts worth of tidal projects scheduled to start up in South Korea by 2010, 2015. Now, you've hardly heard about this, I'm sure, but this will be the biggest some of the biggest new renewables established in the world. I mean, we're still discussing, after 100 years of discussing possibly doing something about our tidal resource in Britain, and they actually started 2 years ago and said, right, we'll have 2.5 gigawatts installed by 2015. So here's a mechanical, arithmetical thing. If you run up renewables by 5.2% per year, average, and you assume demand goes up by 2%, you can actually meet each other and let all the others, coal, oil, gas and uranium, go to zero, roughly, by 2050. So this is the test. Well, can you get 5%, 5.2% growth? Well, Germany's been getting 20s and 25% growth in wind for the last couple of years. Other countries perhaps not as well. 5% globally is pushing it, but it's not crazy. You know, you can't say, well, that's completely out of, you know, it's conceivable to imagine if you happen to want to press all the right buttons to do what I was saying, at 100% by 2050. I'm not saying it's going to happen, but I'm saying this is a simple test. It's not obviously stupid as a perception. Except and unless you look at the reality, and here's where we are at the moment. The European Union set us a target of 20% by 2020, and here we are, just beating Luxembourg and Malta. So you should feel pleased about that. Down the other end, you've got Sweden, Finland, Latvia, and all the others. So we have a long way to go. Our target is 15% by 2050, and we're at 1.3, or probably, this is 2003 or 5. We're about 2% now. We've crept up a bit. Things are not good in this country. So maybe we'll have to rely on other countries a bit, not just for Europe, but to have a Europe-wide sharing arrangement. An international power grid. Could be electricity, but could also be hydrogen. People have said which type of transmission is most efficient. There's some attractions in hydrogen. Shoot it along pipes. People have argued that we've actually moved from solid historically through to liquids and to gas. We started off on wood and coal and then moved to oil and liquids, and then gradually moved to methane and hydrogen. This is a logical, technical progression. The trouble with hydrogen is the use from vehicles, which is the most obvious one. Direct wind to car battery, 86% efficient. Indirect wind to electrolysis, to hydrogen, to electrolyzer, to fuel cell, to vehicle, 25% efficient. Once you start playing the complicated technologies and switching between media, rotation, electricity, hydrogen, back, forward, you start losing energy on the way through. You can rescue some of that energy, actually, but even so, it's beginning to look that electricity transmission and electricity will continue to be the end use that we'll use. And of course, once you start thinking out of the box of national economies, we do this. Solar in the desert. Wind in the North Sea, hydro in the north, biomass in the middle. Use the country's strengths, each country's strength, and balance it out by a huge interchange of energy on a high voltage DC supergrid. In the south, you've got solar in the desert. These are focused mirrors on a power tower with a big molten heat store. So you store some of the heat overnight to carry on running steam into a turbine so it can run 24/7. Half a dozen of these being built as we speak. There's connections being built across the Mediterranean, from the ones in Morocco, Algeria, Tunisia, wherever. This is the one that's being built at the moment, going up into Germany. Big, concentrated solar power is reckoned to be the future. Disadvantages and advantages. Low transmission losses, because it's high voltage DC, so maybe only 2% for 1,000 kilometres. Probably makes sense to get solar energy where it is. It's hard in in Aberdeen, easy in the desert, do it there. On the other hand, this could be an excuse for us not to do anything here. Oh, we'll just carry on buying in power from outside like we've always done. We'll switch one lot of Arabs in one bit of desert to another lot of Arabs in another desert, supply us power. This is, maybe a good thing. If it was fair traded, this might help the North African area to develop its economy. Maybe this is something we should be doing. On the other hand, we could be cut off suddenly by the Algerians suddenly pulling the plug on us in Northern Europe. People are talking about something like a 20% supply from outside of Europe. We've got our own internal stuff. This is the supergrid offshore suggested by Airtricity. Another version of the same thing. And the reason we're talking this way about integrating Europe is because this is where a lot of power's got, in the form of gas and going to be coming from down here. And of course the Chinese over here also want this stuff as well. So this is not going to be very stable in the long term. So if we're going to not be able to rely on this particular grid, we've got to build a new one, which is fed from power from another point. Well, the North Sea is one place, we've got all that wind. But also not just Europe, the old Europe, the new Europe has a lot of offerings. Just at the moment, just a simple example, Bosnia-Herzegovina, Croatia, Macedonia, all running at percentage electricity shares much higher than many other countries in Europe. If you look at the resource potential, I know we're running out of time.
You have run out of time.
Yeah. Huge resource wind potential for some of the new European countries. The point I'm going to make is that if we move outside Europe as well, even larger, Kazakhstan, Turkmenistan, all those, I can imagine in 10, 15, 20 years, the peripheral areas of Europe, some of the stands, North Africa, will be the main energy suppliers. We'll be having this huge energy grid around the country, supplying us with southern Morocco. Just come back from there. Huge amount of wind potential. This is changing the whole perspective. Our whole view is, Eurocentric. Once we start thinking outside of the European belt, things are going to look very different. Geopolitical issues, as the Legion, just think your way through. The whole politics is going to change. European Union's keen on doing this to some extent. It allows you to import power by various means, emission credit systems and joint implementation and CDMs and all that. Should we do it? Well, we're arguing about whether we should allow countries to import power and not do it themselves, which lets them off the hook. But it really doesn't matter where you make the carbon savings, actually, as far as the planet's concerned. You do it cheaper in Albania, you do it in Albania. It's the same carbon that's not being emitted wherever it comes from. Quick final conclusions. Small can be okay, but you probably need a supergrid to glue the whole thing together. It's a bit like information technology. We started off with large, big machines, broke it down to decentral PCs, and then glued it all together again with the web. Maybe we can do the same with energy. Supergrid would allow local stuff to supply and help balance variations across a wide area. You can have interaction between the small grid and the larger demand system. So there's a lot of possible issues. The whole thing could look very different in 15 years' time. And we don't know how this big system will actually operate. It's a very new area. The emergent properties of this new system are sort of thing we can discuss. European Union is pushing ahead to quickly go through. A couple of weeks, months back now, they announced 100 million, another 150 million for various bits of the supergrid to be installed. Companies are lining themselves up to get the money. This is the Norwegian company, Emira. There's their plan, the first part of the grid, offshore, picking up offshore wind. And another company, Mainstream, which is an actually offshoot of Airtricity, has its own supergrid. Right, we're going to see supergrids being the colour of the future. To finish off, Obama saying the same thing for America. So the supergrid issue, I think, is going to get very big because it changes if you can cope with the geopolitical negotiation issues. I know I'm well over time, so I'm going to stop there.
Thank you very much indeed.
While we're changing over, can you put the next one on? Anybody who needs to sit down, find a seat. Also, did you have any points of clarification for David? Because we will leave the discussion after Stephen's presentation.
Yeah.
No, it was just a general question regarding wind power, because it's a lot of subsidies involved in at this point in wind power, and in your calculations and showing wind being one of the main future options, how much would that mean government subsidising this and taking money from somewhere else?
Subsidies for wind power.
Subsidies?
Government.
The simple story is everybody else in Europe except Britain uses a system which works called the feed-in tariffs, which is why Germany's got 24 gigawatts and Britain's got 2. We use a perverse system which costs about 40% more per kilowatt hour of energy generated for reasons I can't understand. Is that an answer? And there's no actual subsidy, it's passed on to consumers. The consumers pay in Germany about 5% more on their electricity for the wind programme. In this country we're paying twice as much, effectively, for a much smaller programme due to the perverse system we've got. But it's still a small amount of extra power. There's no government subsidies involved. Government is not subsidising renewables in England at all. There's no... Yeah.
Great, thank you.
May I have a quick?
Very quick, yeah?
Yeah.
We will have questions
Okay.
after the second. It's only for clarification.
Yeah.
Right.
For
Okay,
David.
just you were talking about the bigger Europe, so Bosnia-Herzegovina and all that, they are at 10-12% of renewable, but that's basically only large hydro, and they are basically saturated, so they struggle to increase even by 1% in the last, I don't know how many years. So I don't think that we'll get this 5% growth or whatever kind of growth over there if we don't put massively efforts in. Yeah.
Yep. Yes, I mean, I spent a lot of time in New Europe, and all the new European countries are having a really, increasingly because of the recession, massive effort to try and deal anywhere near the targets they've been given with by the European Union. So yes, I don't see them being able to easily do this, but the potential is there. So if the West, so-called, decides to start investing in the East, then here's a major area. This is an attractive proposition because we just come back from Albania, the team I'm working with, and they're looking to westward to money. So if we're looking for aid, they see this as aid, of course, but aid which could help the planet seems not bad aid.
Great. Okay, thank you very much. So I think...